Today I'm here to shed a light on a critical social issue that often goes unnoticed. This problem is sarcasm, a type of seaweed and its profound impact on our community. Let's first understand why sarcasm is a present social issue. Sargassum blooms, exacerbated by climate change and pollution, are affecting coastal areas, tourism, health, and local economies. The foul smell and unsightly appearance drive tourists away, impacting businesses and livelihoods. The solution lies in utilizing technology to predict and combat sargassum. This is where CubeSat's small satellites come into play. The mission objectives include developing CubeSats equipped with advanced sensors to monitor sargassum movement in a real time and predict its arrival at specific locations.
Hi, this is Johan Dominguez. I will be continuing speaking about mission objectives of the project. Our mission aims to demonstrate the effectiveness of a system of compact satellites equipped with the Hyperscape 100 spectrometer in achieving sargassum monitoring without the need of bulky and obsolete equipment. Our mission objectives are first, comprehensive monitoring of sargassum. We will focus on monitoring sargassum throughout its life cycle, covering its behavior, propagation, fertilization, and decomposition. Second, health impact research. In addition, we will conduct research of the health impacts of sargassum gaseous emission, including methane, ammonia, and hydrogen sulfide, with the aim of assisting health authorities in risk management. Number three, environmental change analysis. We will also evaluate the role of sargassum in environmental changes, in particular, its influence of water temperature and its possible contribution of methane emission associated with global warming. Number four, scientific impact. We will use a modern high-tech spectrometer to monitor sargassum, raising the quality and precision of the data. Number five, technological impact. The Sargassum 1 mission marks a significant technological advance compared to current technology used for sargassum monitoring, such as the Sanitel-2 and Sanitel-3 satellites, as well as other systems such as the NASA and USGS Sargassum Wedge System, SAWS. Last but not least, we also have social and economic impact. Our mission has a far-reaching social impact by addressing the challenges that the sargassum proliferation has imposed on the Dominican Republic and the Caribbean. Concept of operations. To achieve our objectives, it's essential that our mission follows the following steps. Phase 0. Design and manufacturing. The starting stage for the correct deployment of its mission is the construction of the satellites adjust to our 3 units with their respective propulsion system for the end of their useful life. Phase 1. Sending the CubeSat constellation to space. Our goal is to launch our constellation via the International Space Station in 2028, aiming for a 400-kilometer orbit. Our guidance, navigation, and control system will position the constellation in a polar circular orbit at 750-kilometer altitude, with an elevation of 14 degrees and inclination of 57 degrees. Phase 2. Data acquisition. Once deployed, the constellation CubeSat will continuously monitor sargassum at 6-hour intervals, providing near real-time data. Phase 3. Data transfer. Data transmission will be carried out using 9,600 bits per second half duplex UHF radio with a monopole UHF loop antenna. We have partnered with SatBox. Phase 5, an end of life and replacement. We will arrange a controlled descent of non-functional satellites and ensure timely deployment of replacement to maintain uninterrupted data transmission. At the end of the useful life of the CubeSat, they will be reposed through integrated propulsion system to the graveyard orbit, which is 36,000 kilometers above the Earth.
Talking about now the CubeSat design and its key performance, achieving precise spatial resolution between 90 and 100 meters is crucial for this sargassum monitoring. This enabled the detection of even the smallest accumulation of sargassum, ensuring the detailed observation and accurate identification of high concentration areas. The satellite spectral analysis capability is around 242 to 664 nanometers, and this allows us to learn about the different species of sargassum based on their unique spectral signatures in the photobiological radiation zone, which is about 280 to 800 nanometers. To get a comprehensive view of the sargassum behavior, Data Fusion integrates information from diverse sources, including satellite imagery, oceanographic, and meteorological data. This synchronization provides a contextual representation of the sargassum in the ocean, as you can see in the bottom pic. For valuable insights, efficient high-speed data transmission is vital. Broadband transmission within specific transfer rate ranges ensure timely delivery of the monitoring data. The second point that I want to talk about is the space segment of the CubeSat design. To guide our mission, we will describe a conceptual design for our satellite, opting for a practical and cost-effective 3U CubeSat with applications and sensor systems for sargassum research. Following NASA guidelines, each 3 CubeSat measures about 30 per 10 per 10 centimeters, or a volume of 3,000 centimeters cubic, and it weighs around 4 kilograms. As well, it will include a propulsion module PN200, and that will allow us to put our satellite in orbit. And on the end of the life cycle, we'll go to the satellite's graveyard, which is around 36,000 kilometers apart. In a 750-kilometer orbit, the power of the solar cells is not continuous due to the solar eclipse, of course. And our period of the satellite will be around 100 minutes, and the total solar eclipse will be around 38 minutes. And this configuration will give us 6 watts per hour of generated power, and the total system consumption is approximately 60 watts per component. Going back to the propulsion model, using the propulsion model will be the satellite will go on the specific orbit that we design, and the required delta V from a 400-kilometer orbit to a 750-kilometer orbit will be around 186.60 meters per second. And this is using data from SpaceX or the International Space Station. Now, moving on with the orbit and constellation description, selecting the mission is important to delimit the zone of analysis. We know that the sargassum area has a large coverage along the Atlantic Sea, making it one of the largest concentration of algae around the world. It is approaching to have more than 5.2 million square kilometers, and due to the mission's nature, a circular polar low Earth orbit LEO at a 750 kilometers of altitude, 13.5 degrees of elevation, and 57 degrees of inclination has been selected. This setup will give us a radio of coverture of 1,782.9 kilometers, and the area obtained will be more than 8 million kilometers square. And notice now that the area of coverture is larger than the sargassum sea. And this is because we want to provide as much data as possible between periods and making it more effective. Of course, it's not possible to have a continuous data with just one orbit. We must set a constellation of satellites to provide proper continuous data stream with no blind spot of the sun. For our mission, we are going to use a cluster Walker Delta constellation, which follows the principles of an orbit, of a polar orbit with a certain amount of inclination. This constellation allows us to have continuous data for our configurations. To keep the cost of the mission as economic as possible, we are going to use a Walker Delta pattern of 57 degrees of inclination, 6 satellites in total, with 3 planes of orbit distributed around the satellites, and 1 relative spacing between the satellite in adjacent planes. This pattern will allow us to have continuous data stream with no blind spot whatsoever.
Implementation plan. We are going to talk about funding, breakdown of the mission cost, timeline, and challenges. In collaboration with the Ministries of Environment, Higher Education, Science and Technology, Energy and Mines, and Tourism, we are seeking funding to carry out this initiative. Although the allocated funds may not fully cover our cost, we plan to develop and test the CubeSats in our UNISEC laboratory, which is fully equipped, and we have a manpower of 10 people working on this project, divided by teams based on their strength and knowledge. Our mission's total cost will be $397,731.87, plus an extra 30% due to taxes and surcharges. This will cover the CubeSat's structure, microchips, the communication system, the power system, telemetry, and the CubeSat's deployment. Our project spans from October 2023 to October 2032, with 108 months dedicated to planning, development, launch, and data acquisition. The key milestones are in the first 4 years, from sargassum research to requesting quotes to select the launch agency in February 2024. We face several challenges, from financial limitations to potential disruption from solar events and the International Space Station transition. We have developed a mitigation plan to address these challenges, which leads to ensuring the continuity of our operations. In summary, Sargassum-1 utilizes CubeSats with a Hyperscape 100 spectrometer to monitor and address sargassum issues in the Caribbean. With a focus on real-time data, health impacts, and economic implications, the project offers an innovative solution. And despite potential challenges, the predictive risk management approach underscores its commitment to success. Overall, Sargassum-1 is a vital initiative in mitigating sargassum's impact in the region. Thank you so much for your attention.